Okay, we've been talking about seasonal changes the last few days. Here's one of the worksheets that we went over in class. As we started looking at this worksheet, it's talking about the different seasons. We see the spring and the fall equinox, and we see with those we would expect equal hours of daylight and equal hours of darkness. Obviously with our summer we expect more hours of light, and in winter we expect more hours of darkness. As we go down further on the page, we can see as we're looking at the different questions on here, the question was asking about Berkeley, California, and that's the dotted line going around here. If we were showing Berkeley, California in the summer solstice, we would see that the line between day and night would fall straight down the middle, okay, from the top down to the bottom, showing more of the dotted line on the daytime side and less of the dotted line on the nighttime side, which would be right for the summertime, and we expect them to have, like it says here, 14 hours or so, or a little more than 14 hours of daylight, and that's what the circle is showing us. And then if we go down to the next question here, question 5, it's talking about where the line crosses Berkeley for the spring equinox, and we can see it goes across from the left to the right. With the spring equinox, we want to have, again, equal hours of daylight and equal hours of darkness. So we want to cut the circle right in half, half of the circle in daylight, half of the circle in darkness, and we can see with the dotted lines, that's exactly what we have here. If we flip over to the back side of that page, there's a couple questions on here going over some common things that are misconceptions with the seasons. We have some incorrect student responses, and we went over these in class. If the student had an incorrect response that read something like, the reasons for the season is that Earth revolves around the sun in an elliptical orbit, and when it's farthest from the sun, it's winter, and when it's closest from the sun, it's summer. That's incorrect because the seasons don't have an effect on the distance we are from the sun, and Earth's orbit's only slightly elliptical, so there's not really a big change in our distance from the sun. So the diagram here is way over exaggerated. That sun should be much more in the center, and the effect on the seasons, the main thing is the tilt of the northern pole towards or away from the sun. When we look at another question with some misconceptions on here, we have another student, and what this student here in the second one is looking at is about facing the sun and calling it summer, and facing away and calling it winter. And what they're doing is they're confusing summer with daytime and winter with nighttime. So in this one, the North Pole is still facing away from the sun. So because that North Pole is facing away from the sun, even though they are on the side facing the sun, that would be daytime in the winter, and this one would be nighttime in the winter. So they've confused the difference between day and night with the tilt of the poles, which causes the change in the seasons. And with the third question here, they're looking at the tilt is always towards the sun. Well, that's incorrect. We say that the tilt is always towards the North Star or Polaris, not always towards the sun. Otherwise, it would always be summer. And then they have here, it takes 365 days for the Earth to rotate. Well, that would be revolve. They confuse the word rotate with revolve there. And then again they make the same mistake here. So when we were on the side towards the sun, it is summer, that's just daytime, and when we were on the side away from the sun, it's winter, that's just nighttime. So they make some of the same mistakes as the second one did there at the end. One of the next things we talked about in class was solar angle. Here we have an example of low solar angle. With low solar angle, we're going to get a very, very large beam spreading. Okay, not a lot of solar energy entering each one of these compartments, only one ray of sunlight delivering energy particles to the surface in each one of these divided up segments. When we look at the opposite of that, we'd see a high solar angle. We get a lot more concentration of solar energy delivered to each little segment or divided up area. So high solar energy, or energy coming straight on, when we did the circle on the chalkboard, this was the smaller circle. We said that this would be summertime. We're seeing the particles closer together, more compact. Okay, when we look back at this low solar angle, this would be the stretched out or elongated circle that we tip the flashlight to the side, okay, which would give us more spread out energy over a larger area, but not as concentrated. More winter, okay, and again, more summertime. We also took a flashlight and shined it on the globe. We've seen the same thing happen that this diagram is showing us. When we shine the flashlight right on the equator over the middle of the Earth, it was very, very concentrated and very, very small. As we started to move the flashlight, and we didn't change our distance of the flashlight from the globe, we just moved the flashlight up and down. As we move the flashlight up and down, we can see that the circle starts to get elongated. Because the Earth is curved, it works like taking the flashlight that we shined on the chalkboard and tipping it down to the side. So as we get closer to the edges of the Earth, the curvature of the Earth works like tipping the flashlight to the side. When we shine the flashlight straight down on the chalkboard, then it's like shining the flashlight straight onto the equator, and it's very, very concentrated. So we get very, very spread out right around our sunrise and sunset sides of the Earth, and then we have the poles getting their very, very spread out weak solar energy because of the curvature of the Earth, and we have the areas around the equator and around the middle of the Earth more where the sun is shining at a very, very high angle, close to 90 degrees, delivering concentrated solar energy. In class, we looked at this worksheet for beam spreading, where we shine the flashlight on the board, and we talked about how the solar angle and beam spreading have an effect. So with this one, how do we explain the different shapes of the spotlights? Well, when we shine the light straight on the chalkboard, it was at 90 degrees, and it didn't spread out much. It was a very circular shape. When we tipped the flashlight to the side and we got a smaller angle, it gave us a oval shaped or an elongated circle. So we could see here in the answer, as the angle gets smaller, the light spreads out more on the surface, making it larger and more of an oval. Okay, when is the area of the spot the largest? The spot's the largest when the solar angle is the smallest. Okay, as we tip the light more, it makes a larger oval. When we shine the light straight on, it makes it a very, very small condensed spot. Looking at question 3, which spot delivers the greatest amount of energy to, in this case, not the floor, but the chalkboard? They both deliver the same. The smaller spot does more energy for that area, but they both deliver the same amount of energy. It's the same flashlight from the same distance away. We use the meter stick, so we taped the flashlight or held the flashlight to the meter stick, so the light was held the same distance away from the chalkboard, so it's delivering the same amount of energy. Now, remember that the smaller spot will have more energy per inch or per area, but that really applies more to question 4 here. If you put the penny in each spotlight, which we did do, which one will receive the most energy? The penny will receive more energy placed in the smaller spot. The light density is greater when it shines directly down on the surface, and there is no beam spreading. So when we have less beam spreading or smaller beam spreading, the solar energy or light energy is more concentrated or compact and close together. So more energy particles would be closer to that penny or touching that penny. So that's why the straight down light would shine more on the penny. And how does this affect the Earth? Okay, so what influence does solar angle have on heating the Earth? Solar angle influences the Earth, how much energy is received in an area. A large solar angle means that more energy per unit area on the Earth's surface. Okay, it's very, very concentrated. We're getting more energy to a single spot on the Earth. Okay, where we have a small solar angles results in beam spreading, where it gets stretched out over the surface, like we talked about before, looking at the poles and towards the sunrise and sunset sides of the Earth, the far east and far west, delivering less solar energy in the surface of the Earth. So that energy is spread out more, it's not as concentrated, not as direct. We talked about in class an example, like if we were to give out $100 to divide that up amongst everybody sitting in the front row of class. We said that the students would get maybe anywhere from $12 to $14 depending on how many students were sitting in the front row. If we were to take that money and divide it up to everybody in the class, that same $100, if the class had 20 students in it, then everybody would get $5. But most of the classes had closer to 25 students in it, so the students would get more like $4. So we get 3 times as much if we are concentrated and just divide it up to the front row. If we divide it up to the whole class, that's 3 times less for everybody, or it's a third of what everybody else would get if it's spread out over the entire class, not as concentrated. In class we also looked at this diagram. With this diagram, it does a very, very good job of showing the sun's path through the different seasons. So when we look at this in December or in winter, we see the sun is very, very low in the sky, doesn't get to a very, very high angle. So because it's at a low angle, we're going to get a lot more beam spreading taking place, very, very weak sunlight, not delivering a lot of concentrated energy, so it's not going to heat up the Earth very much. It also is a very, very short path in the sky, so it's not going to be in the sky for very many hours as we are looking at that path. Okay, we can see it as a very, very short path, so it's not going to be in the sky for very, very long. When we look at the opposite of winter, when we look at summer, it is a very, very long path in the sky, which means that the sun will be in the sky for a longer period of time. More hours of sunlight. More hours of sunlight will allow the sun to heat the Earth up more. We also see that the sun is higher in the sky. Because the sun is higher in the sky, it's going to be shining down at a higher angle, less beam spreading, more concentrated solar energy. Because we're getting more concentrated solar energy, it's going to heat the Earth up faster. So there are a couple reasons why in the summer we get the warmer temperatures. Okay, we are tilted towards the sun with the northern hemisphere. Because we have a tilt on our axis, the sun doesn't stay in the same place in the sky as we go around the sun as we revolve. Okay, the sun is going to move to different heights. In the summer, very, very high. High sun gives us a very, very high solar angle, low beam spreading, very concentrated solar energy, heats up the Earth more. Also giving us a very, very long path through the sky, giving us more hours of sunlight for the sun to heat the Earth. We have our equinox in spring and fall. We have the sun moving through a somewhat medium path, where it is moving through the sky not too long but not too short, and at a decent angle in the sky where it's giving some concentrated rays of sunlight, but there is some beam spreading that is taking place, and it is not as concentrated as summer, where we see a very, very high angle in summer. We see a little weaker angle in the spring and the fall. And then finally again in winter we see a very, very low angle and a very, very short amount of sunlight. And with that low angle and short hours, the sun does not have time to heat up the Earth, and it doesn't have the concentrated energy to heat up the Earth. So we get colder temperatures. If you have any questions, make sure to stop in and ask, or ask before the test tomorrow. Have a good night.